Something is loading beneath the surface of the tropical Pacific right now that should stop you. Not in a year, not next season. Right now, in the final days of April 2026, a column of water sitting between 100 and 250 meters below the equatorial Pacific surface is running 6 to 7 degrees Celsius above normal. That warm water mass carrying more thermal energy than any subsurface anomaly measured at this stage of El Niño development in the modern satellite era is moving east. It is moving at the pace of a Kelvin wave, which is to say, invisibly, steadily, and with the full physical certainty of a wave that has already been launched and cannot be recalled. It does not respond to press releases. It does not respond to model revisions. It does not pause while agencies update their seasonal outlooks. The eastern Pacific coast of South America will feel its arrival, whether or not a single headline adequately describes what is happening right now beneath the surface of the world's largest ocean. A second Kelvin wave has already developed in the western Pacific and is moving into position behind the first one. The system is not firing a single shot. It is loading a second round before the first has landed. This is how the strongest El Niño in decades begins. Not with a dramatic announcement from a government agency, not with a news alert about extreme weather. With water moving underground through the thermocline, in the dark, at jogging speed, carrying enough thermal energy to reshape the weather of every continent on Earth for the next 12 to 18 months. NOAA's Climate Prediction Center, as of April 2026, gives El Niño a 61 to 70% probability of formally emerging by June through August of this year. The European Centre for Medium-Range Weather Forecasts, the gold standard of global seasonal climate modelling, places its median forecast for the Niño 3.4 sea surface temperature anomaly, the primary index used to score El Niño events, at plus 2.2 degrees Celsius by September 2026. A reading of plus 2.2 degrees Celsius would place this event at or above the 1997 El Niño, the strongest ever recorded in the modern observational period. It would make this the most powerful El Niño the planet has experienced in at least 29 years. Some ensemble members project higher. And this event is arriving on an ocean that has never, in 174 years of recorded climate data, been this warm to begin with. The Niño 1+2 index, the sea surface temperature measurement covering the far eastern equatorial Pacific, the zone closest to the Peruvian and Ecuadorian coastline that warms first and fastest when El Niño arrives, already reads plus 1.8 degrees Celsius as of the week centered on the 15th of April 2026. That is not a projection. That is a measured, current reality sitting in NOAA's observational database right now. The far eastern Pacific is already nearly 2 degrees above its historical average before the event has formally been declared, before the trade winds have fully reversed, before the main body of the warm water anomaly has even arrived at the South American coast, before the event has peaked or anything close to it. The last time the Niño 1+2 region ran this warm this early in an El Niño's development was during the build-up to 1998. What is coming is not a weather disruption. It is a planetary-scale reorganization of heat and moisture that will touch every continent, every ocean basin, every food system sensitive to tropical Pacific sea surface temperatures, which is to say, most of them. And it is not weeks away from beginning. It began in the water months ago. The surface has simply not caught up yet to what the subsurface is already doing. To understand why this specific event, at this specific moment in time, matters so profoundly more than its historical analogues, why the ECMWF median forecast of plus 2.2 degrees is a different kind of number than the same anomaly would have been in 1997, you need to understand too. Separate things simultaneously. You need to understand what El Niño actually is at the physical level, down to the specific mechanics of how it moves heat across an ocean basin. And you need to understand what has changed about the ocean it is about to operate in. Because those two facts together tell a story that neither one tells alone, and it is a story that the simplified El Niño coverage cycle does not have adequate space to convey. Start with the mechanism. El Niño is, at its core, a disruption of the Walker circulation. The Walker circulation is the atmosphere's great equatorial engine, a vast closed loop of air that circuits the tropical Pacific, driven by the temperature contrast between the two ends of the ocean. On the western end, the deep, warm waters of the western Pacific warm pool near Indonesia and Australia produce intense evaporation, fueling towering thunderstorm systems that release enormous amounts of latent heat into the upper troposphere. That released heat drives the air upward and outward, where it flows eastward at altitude across the tropical Pacific until it reaches the eastern Pacific, cools, and sinks, producing the persistent zones of high pressure and suppressed rainfall that characterize the equatorial eastern Pacific under normal conditions. At the surface, the eastward flowing air returns westward as the easterly trade winds completing the loop. Those trade winds do something physically remarkable. They drag the warm surface water of the tropical Pacific westward as they blow. The cumulative effect of this continuous westward drag is the maintenance of the Western Pacific warm pool, one of the largest and most thermodynamically energetic bodies of water on Earth. Surface temperatures in the warm pool routinely exceed 29 and 30 degrees Celsius, which is 84 and 86 degrees Fahrenheit. In terms of total heat energy, the warm pool stores more than any comparable ocean volume on the planet. It is the engine's fuel tank, and the trade winds are constantly refilling it by dragging warm surface water west from the central Pacific. At the eastern end, the same trade winds maintain the ocean's cold upwelling system. As the trade winds blow westward along the equatorial surface, they drag surface water away from the South American coast, a process called Ekman transport. To replace that departing surface water, cold water from depths of 100 to 200 meters rises to fill the gap. This upwelling produces the cold tongue, the persistently cool band of water that extends westward from the Peruvian and Ecuadorian coast along the equator, running 5 to 10 degrees Celsius cooler than the warm pool at the western end of the basin. The cold tongue is not incidental to the climate system, it is structural. The east-west sea surface temperature gradient between the warm pool and the cold tongue is what gives the Walker circulation its driving force. Warm ocean produces rising air. Cool ocean produces sinking air. The pressure difference between them drives the trade winds. The trade winds maintain the warm pool and the cold tongue. The engine produces the fuel. The fuel drives the engine. When this system weakens, and it weakens periodically, for reasons rooted in the internal variability of the climate system that researchers are still working to fully characterize, everything changes at once. The trade winds slacken. The force that was holding the warm pool water against the thermocline's tilt relaxes. An enormous mass of warm water, no longer pushed westward, begins moving east. Specifically, it moves east in the form of Kelvin waves, subsurface equatorial waves that propagate along the thermocline at approximately 2 to 3 meters per second, covering the full width of the Pacific, roughly 12,000 kilometers, in approximately 2 to 3 months. Kelvin waves are invisible from the surface while they are in transit. They carry their thermal cargo below the top layer of the ocean, where standard sea surface temperature measurements are taken. A buoy at the surface would not detect them passing beneath it. What does detect them is the TAO, Triton Mooring Array, the grid of anchored oceanographic buoys that NOAA and partner agencies maintain across the tropical Pacific, stretched from Indonesia to the South American coast, each buoy measuring ocean temperature, salinity, and current velocity at multiple depths simultaneously and transmitting that data to shore via satellite every day. The TAO, Triton network, was built specifically because of a forecasting catastrophe. In 1982, one of the strongest El Niño events in the modern record developed and peaked without a single major forecasting agency detecting it in advance. The event killed approximately 2,000 people and caused $13 billion in damage. It was not predicted because the subsurface data did not exist. There were no deep ocean sensors in the tropical Pacific to detect what the thermocline was doing. The event blindsided the entire climate science community, and that humiliation produced the political and scientific will to build the network that now watches every millimeter of thermocline movement across the equatorial Pacific in near real time. That network is what caught the current event in the act of loading. Buoys along the equatorial Pacific transect at 0 degrees latitude have been recording anomalously warm subsurface temperatures strengthening and migrating eastward through early 2026. The warm water anomaly, at depths of 100 to 250 meters, sitting just above and in the thermocline layer, peaked at 6 to 7 degrees Celsius above normal as it passed through the central Pacific. To translate that number into physical terms, the thermocline in the equatorial Pacific is the layer where temperature drops from roughly 28 degrees at the surface to roughly 8 degrees at depth over a vertical span of about 100 meters. A 6 to 7 degree warming of the water in and just above that layer means the thermocline itself is suppressed, pushed deeper by the arriving warm water mass, which means the cold upwelling that normally brings cold water too. The surface on the eastern side is being suppressed as well. The effect propagates eastward with the wave front. Where the wave goes, the cold tongue retreats. Climate Impact Company, an independent climate analytics firm tracking the TAO, Triton data in real time throughout 2026, characterized the subsurface heat content as immense in its March 2026 diagnostic report, noting that a second Kelvin wave had already initiated in the western Pacific behind the first, suggesting the system was not delivering a single pulse, but a sustained transfer of warm water volume to the east. The last time the equatorial Pacific subsurface heat content was loaded to this level, at this stage of an El Niño development cycle, was prior to one of the 3 strongest events in the modern record. The trigger that launched this system was the rapid collapse of the La Niña that preceded it. The 2025-2026 La Niña, the cold phase of the El Niño southern oscillation cycle, during which the Walker circulation strengthens, the trade winds blow harder than normal, cold upwelling dominates the eastern Pacific, and the world's atmospheric circulation tilts toward its cool Pacific configuration, peaked in mid-2025 and held through autumn before beginning to weaken. The pace of its dissolution was faster than the model consensus had anticipated. Negative sea surface temperature anomalies in the Niño 3.4 region, which are what sustain La Niña conditions, largely disappeared by February 2026. The weekly Niño 3.4 reading turned positive in March. By April 15, the index sat at plus 0.5 degrees Celsius, exactly at the threshold of official El Niño watch territory, moving upward. A La Niña that collapses rapidly tends to transfer more energy to the following El Niño than one that decays slowly. The mechanism is straightforward and is grounded in the same physics that describes a wound spring releasing. During La Niña, the anomalously strong trade winds accumulate warm water in the western Pacific warm pool beyond its normal level. The longer and more sustained the La Niña, the more warm water is piled up in the west. When the La Niña ends and the trade winds relax, that excess warm water more than the normal level is what flows eastward as the initial Kelvin wave. A rapid La Niña collapse means the relaxation of the trade winds happens faster, releasing the accumulated warm water more abruptly and energetically than a gradual transition would. The result is a more intense initial Kelvin wave pulse. The 2025-2026 La Niña was not extraordinary in its peak intensity, but it maintained negative anomalies for long enough to accumulate a significant warm water reservoir in the west before its rapid collapse transferred that reservoir eastward as the most energetically loaded subsurface anomaly currently active in the equatorial Pacific. The warm water volume anomaly in the upper 300 meters of the tropical Pacific, the metric NOAA's Climate Prediction Center tracks as a leading indicator of El Niño intensity, is currently elevated above its historical mean for this time of year. The system has more thermal ammunition loaded than the average El Niño year at this stage. The spring predictability barrier, the period in April and May when ENSO forecast models are least reliable because the equatorial Pacific is in a transitional state and small differences in initial conditions propagate into large differences in outcome, means the forecast range for peak intensity is wider than it will be in a few months. That range currently spans from a moderate event on the low end to a super El Niño exceeding plus 2.5 degrees Celsius at the high end. The ECMWF median sits at plus 2.2 degrees. What every model in the multi-agency ensemble agrees on is the direction. None of that trajectory can be understood in its true significance without understanding what has happened to the ocean that the event is traveling through. The global ocean in 2024 and 2025 ran warmer than at any comparable period in the modern satellite-era observational record. The pattern that first became apparent in 2023, when global sea surface temperatures began setting records across multiple ocean basins simultaneously, not just in the El Niño monitoring region, but across the North Atlantic, the South Atlantic, the Indian Ocean, and the Southern Ocean, has persisted. The North Atlantic maintained anomalously warm surface temperatures across 2024 and into 2025 at levels that, had they occurred in a single year, would have been described as extraordinary. Occurring as a sustained multi-year feature, they suggest that something in the baseline state of the global ocean has shifted. The physical significance of a higher baseline temperature for El Niño is not intuitive on first encounter, but it is mathematically precise. The Niño 3.4 anomaly score, the +2 or +2.2 or +2.3 number that agencies use to classify event intensity, is a departure from the 1991 to 2020 climatological mean. But the biological and physical thresholds that El Niño actually crosses when it arrives are not departure sensitive. They are absolute temperature sensitive. Coral bleaching begins when sea surface temperatures exceed approximately 1 degree Celsius above the mean monthly maximum temperature for a given reef system, sustained for more than 4 consecutive weeks. That threshold is an absolute temperature, measured in degrees Celsius, not a departure from a baseline. When the baseline rises, when the mean monthly maximum for a reef system in November is 0.3 degrees warmer than it was in 1997, El Niño's anomaly of +2 degrees reaches a higher absolute temperature in November than a +2 anomaly in 1997 did. The bleaching threshold is crossed earlier in the event's development. It is sustained longer because the ocean takes longer to cool back below a threshold that has been set higher. It penetrates deeper in the water column because the warm anomaly is added to a water profile that is already warmer at depth. And it covers more geographic area because reef systems that were marginally buffered against historical events are now within reach of the combined baseline plus anomaly temperature. The same principle applies to the convective thresholds that determine where intense tropical rainfall occurs. It applies to the drought severity thresholds that determine whether a below normal rainfall season produces crop stress or crop failure. It applies to the upwelling temperature thresholds that determine whether the Humboldt Current's anchovy population retreats or collapses entirely. In every case, a higher baseline means El Niño's anomaly reaches more severe outcomes at lower anomaly values than the historical record would predict. This is not a theoretical projection. It has already been documented empirically in the observational record. The 1997, 1998 El Niño peaked at approximately plus 2.3 degrees Celsius in the Niño 3.4 region and produced approximately 21,000 deaths globally and $33 to $45 billion in mass economic damage. It set a global annual temperature record in 1998. The 2015-2016 El Niño also peaked at approximately plus 2.3 degrees Celsius, the same raw anomaly intensity as 1997, 1998, and produced a higher global annual temperature than 1997's event did, despite being equally intense. It killed approximately 15% of the world's coral reefs in the third global coral bleaching event and produced the single most damaging bleaching season in the history of Great Barrier Reef monitoring, with approximately 30% of the northern section of the reef dying in the 2016 bleaching season alone. The 2023-2024 El Niño peaked at approximately plus 2 to 2.1 degrees Celsius, measurably weaker than both predecessors in anomaly terms, and produced a global annual temperature higher than either of them. The 2023 annual mean, as logged by the Copernicus Climate Change Service, was 1.45 degrees Celsius above the pre-industrial baseline, the first year in 174 years of measurement when every single calendar day exceeded 1 degree above pre-industrial average. 3 events: anomaly intensity either matching or declining, global temperature outcomes escalating with every one. The mechanism behind that pattern is precisely the elevated baseline. The 1997 event operated on a baseline that had already risen above the mid-20th century mean. The 2015 event operated on a baseline higher than 1997's. The 2023 event operated on a baseline higher than 2015's. The 2026 event is being projected to reach anomaly values at or above any of those predecessors on a baseline higher than any of them. If the ECMWF median forecast of plus 2.2 degrees Celsius materializes on the current ocean background state, the absolute sea surface temperatures reached across the tropical Pacific this year and into 2027 will exceed what any previous El Niño has produced in the modern record. Carbon Brief's analysis, published in the final week of April 2026, places 2026 as virtually certain to rank among the 4 warmest years in recorded history, with a 19% chance of surpassing 2024 as the single warmest year on record. And that analysis incorporated only the early stage development of the El Niño before its peak intensity had been established. Now go deeper, because there is a structural change happening in the tropical Pacific that most coverage of this event has not yet engaged with, and it is potentially the most consequential piece of the story. The cold tongue, the persistent band of cold, upwelled water that stretches westward from the Peruvian coast along the equator, maintaining the east-west sea surface temperature gradient that drives the Walker circulation, has been warming, not as an El Niño anomaly, not as a short-term fluctuation. As a long-term trend, across multiple decades of satellite-era records, the eastern equatorial Pacific has been warming faster than the broader tropical Pacific average. Analysis of multiple independent sea surface temperature datasets shows this trend clearly. The cold tongue, which normally acts as the cool anchor of the Walker circulation's temperature gradient, is less cold than it used to be on a decadal timescale. The implications of this are significant and not yet fully resolved by the scientific community. The east-west sea surface temperature gradient between the warm pool and the cold tongue is the fundamental driver of the Walker circulation's strength. If the cold tongue warms and the gradient narrows, the Walker circulation weakens on its mean. A weaker mean Walker circulation means weaker baseline trade winds. Weaker baseline trade winds mean less efficient upwelling and less efficient heat packing into the western warm pool during La Niña phases. And a system where the Walker circulation is running at a lower baseline strength is a system where the transition from La Niña to El Niño is structurally easier. It takes less forcing to tip the system from its cold phase to its warm phase. Whether this cold tongue warming represents a transient multi-decadal fluctuation or an incipient structural shift in the tropical Pacific's mean climate state is a question that climate scientists are actively debating and have not resolved. The data trend is real and documented across independent datasets. The physical mechanism by which it would produce the observed trend is understood at a basic level. Whether the trend will continue or reverse, and how far it goes before the system reaches a new equilibrium, is genuinely uncertain. But it is the kind of uncertainty that belongs in every honest account of what is happening in the tropical Pacific right now, because it speaks to whether the El Niño events of the coming decades will be structurally different from the El Niño events of the 20th century. The current developing event is, on the available evidence, forming in a tropical Pacific where the baseline Walker circulation may already be weaker than the historical mean that forecast models are calibrated against. If that is true, the event is starting from a lower resistance state than the historical analog would predict, which is one physical explanation for why the La Niña to El Niño transition has proceeded faster than model consensus. Anticipated. There is an additional frontier consideration that several research groups have raised in the context of this event. The Atlantic meridional overturning circulation, the large-scale thermohaline current system that transports warm surface water northward through the Atlantic and cold, dense water southward at depth, maintaining the temperature patterns that govern European and North American climate, has been documented as weakening across the observational record since the 1990s. There are physically plausible mechanisms by which a weaker AMOC would alter tropical Atlantic sea surface temperature patterns in ways that modify El Niño's atmospheric teleconnection, routing the chain of pressure adjustments that translates tropical Pacific warmth into altered weather thousands of kilometers away over North America, Europe, and beyond. Whether this interaction is currently operative, and whether it is measurably altering the teleconnection geography of the 2026 event, is not established consensus. It is an open research question being actively investigated by several groups using the 2023-2024 event data as a test case. The answer will have practical implications for whether the standard El Niño impact maps for Europe and the eastern United States remain accurate predictors. Now, here is the piece of this developing event that the seasonal forecast documentation discusses in careful technical language, but that has not penetrated the public communication of the incoming El Niño with the weight it deserves. The northeastern Pacific marine heatwave anomaly, the persistent warm feature known informally as the blob, which has characterized the Gulf of Alaska and the US and Canadian West Coast since its initial appearance in 2013-2014 and has re-emerged episodically through the decades since, it remains an active background. The feature of the northeastern Pacific as of April 2026. The blob is not El Niño. It is maintained by a separate atmospheric driver, a persistent ridge of high pressure over the northeastern Pacific that reduces wind speed, limiting the turbulent mixing that normally brings cooler subsurface water to the surface and suppresses evaporative cooling, allowing solar radiation to accumulate in the shallow upper ocean layer. This ridge system is driven by dynamics in the North Pacific atmospheric circulation that operate on timescales and through mechanisms distinct from ENSO. But El Niño's atmospheric teleconnection to North America works through the jet stream. Specifically, it works by displacing the North Pacific jet stream southward, shifting the subtropical jet eastward, and altering the storm track over the northeastern Pacific. When this teleconnection-driven jet stream shift operates against the background of an already warm northeastern Pacific, the result is a hybrid pattern that the canonical El Niño impact map, derived from historical events during which the northeastern Pacific was not anomalously warm, does not predict accurately. NOAA's operational seasonal forecast for the upcoming winter, issued in the early weeks of April 2026, explicitly flags elevated uncertainty for Pacific Northwest and British Columbia precipitation outlooks, noting that the background state of the northeastern Pacific introduces a source of forecast error not present in the historical calibration dataset. This is a technical admission that the simplified El Niño template, California wet, Pacific Northwest drier, Southwest warmer, is not a reliable forecast for the 2026-2027 season because the system now has two overlapping warm ocean anomalies at different latitudes, and the interaction between them distorts the canonical teleconnection geometry. This matters practically for the people and institutions currently making decisions based on El Niño forecasts. Water utilities in Oregon and Washington planning reservoir management. Fire agencies in British Columbia calibrating early season response capacity. Agricultural producers in the interior Pacific Northwest making planting decisions. They are all working from a baseline El Niño impact template that was calibrated on events that occurred in a northeastern Pacific without the blob. The forecast uncertainty is real, documented in NOAA's own materials, and has not been communicated with sufficient clarity in the broader media coverage of the incoming event. In the 2023-2024 El Niño season, when this same configuration, active El Niño plus persistent blob, was last operative, Northern California received near-record rainfall, while significant portions of the Pacific Northwest simultaneously experienced below-normal precipitation. Simultaneous opposite extremes in adjacent regions, both driven by the same atmospheric pattern, expressing differently because of the too warm anomaly oceanic background. The standard template said, California wet, Northwest drier. The actual outcome said, Northern California flooded and parts of the Northwest stayed dry, but not for the reasons the template predicted, and the interior Northwest did not get the enhanced snowpack that the canonical El Niño template would have suggested. The discrepancy was not random. It was physically explainable by the blob El Niño interaction. It was just not widely communicated before the season, and the people relying on the standard template got the wrong answer in places. The blob is still there. The 2026 El Niño is still arriving. El Niño has never operated alone. It operates on a planet doing other things simultaneously, and in 2026, the planetary scale context surrounding this developing event includes several concurrent anomalies that share a time window with the incoming El Niño without being caused by it. Solar cycle 25 is at or approaching its maximum. The solar cycle 25 prediction panel, the joint NOAA and NASA working group that issued a consensus solar cycle forecast in 2019, projected a below-average cycle when the cycle began. The observed sunspot numbers and X-ray flare rates through 2024 and 2025 have consistently run above that projection. The cycle's solar maximum, expected in 2025, based on the one-year cycle timescale, appears to have arrived at or above the predicted level of activity. During solar maximum, the Sun's output of extreme ultraviolet radiation, the high-energy portion of the solar spectrum absorbed in the Earth's upper atmosphere, increases relative to solar minimum. The stratosphere, which absorbs this UV energy, warms in response, the top-down solar influence mechanism, through which stratospheric temperature changes cascade downward through the stratospheric polar vortex and the North Atlantic Oscillation into the tropospheric weather layer operates on timescales of months. The mechanism is physically plausible and has support in observational studies and modeling experiments, but its specific contribution to the atmospheric configuration of any given El Niño season is difficult to isolate from the much stronger ENSO forcing. What is not debated is that the two systems ENSO at maximum warm phase, solar cycle at maximum activity are simultaneously active. Whether they interact and how the interaction modifies El Niño's standard teleconnection pattern over North America and Europe is a question that will take years of post-event analysis to answer with confidence. The Antarctic sea ice system continues to show anomalous behavior that has not received proportionate attention in the Northern Hemisphere media coverage of global climate. Since the Antarctic sea ice extent reached its all-time satellite-era minimum in February 2023, approximately 1 million square kilometers below the previous record minimum, a departure so extreme that the previous record barely appeared relevant, the system has not returned to historically normal levels. Each subsequent Antarctic winter maximum and summer minimum has tracked below the historical mean. The persistent below normal sea ice extent means persistent excess open ocean in the Southern Ocean, ocean that is absorbing solar radiation at latitudes where sea ice would otherwise be reflecting it, releasing heat to the atmosphere above the Southern Ocean and contributing to the elevated global ocean heat content baseline that the incoming El Niño will operate on. The Southern Ocean is warmer than historical norms. That warmth contributes to the baseline. The global ocean heat content as of early 2026, the depth integrated thermal energy in the upper 2,000 meters of the world ocean, measured by the Argo float network, is higher than at any previous point in the Argo era. The Argo float network, which comprises approximately 4,000 autonomous profiling floats cycling between the surface and 2,000 meters depth across every ocean basin, provides the most comprehensive real-time measurement of global ocean heat storage ever assembled. Its data shows a steady and accelerating increase in ocean heat content across the past 2 decades, with 2024 and 2025 values both exceeding all previous records. That heat does not disappear. It sits in the ocean, waiting. When El Niño's dynamics bring it to the surface, or when the anomaly atop the already elevated baseline pushes tropical Pacific absolute temperatures into ranges that trigger bleaching, drought, and atmospheric circulation disruption, the response of the affected systems is calibrated to an ocean that no longer exists. Now resolve this into the specifics of what this means for places and people. Peru's fishing industry is watching the Niño 1+2 index the way any coastal industrial system watches a storm. The reading of plus 1.8 degrees Celsius as of mid-April 2026 is not a comfortable signal for fishing communities along the Peruvian and northern Chilean coast. The Humboldt Current system that sustains their livelihood is one of the most biologically productive ocean systems on Earth, driven entirely by the cold upwelling that the trade winds maintain along the eastern equatorial Pacific. In a normal year, cold, nutrient-rich water rising from depth fertilizes the surface layer with nitrates and phosphates, producing extraordinary concentrations of phytoplankton, which sustains enormous schools of Peruvian anchoveta, the species whose fishery, in a good year, is one of the highest volume single-species catches in the world. When El Niño arrives, the warm water suppresses the cold upwelling. Sea surface temperatures along the Peruvian coast climb from their normal 15 to 18 degrees Celsius into the mid-20s and above. The cold water species anchovy, sardine, jack mackerel have nowhere to go. The fishery can collapse by 50 to 80% in a strong El Niño year. The social and economic consequences fall on coastal fishing communities that have no alternative livelihood, on the national economy of a country where fishing and fish meal production represent a significant portion of export earnings, and through the global fish meal supply chain on the poultry, aquaculture, and livestock industries in Asia, Europe, and the Americas that depend on Peruvian fish meal as a protein input. The Niño 1+2 index of plus 1.8 degrees is the leading edge of that sequence arriving. The fishing fleets off Callao and Chimbote and Paita are monitoring it in real time, and the people making vessel deployment decisions and fish meal contract commitments understand very well what it means when that number is at plus 1.8 and moving upward. Heavy coastal rainfall will follow the warm ocean anomaly along the Peruvian coast. El Niño's atmospheric response to the warm coastal Pacific produces intense precipitation events over regions that are normally desert or near desert, the coastal river valleys of northern Peru, the lowland areas of Ecuador, the arid departments of Piura and Lambayeque that grow rice, corn, and vegetables for national consumption. The same flooding dynamic that produced Peru's state of emergency in early 2024 is in preparation. The question for 2026 is how much warmer the coastal ocean will be when the El Niño peak arrives, and how much more intense the atmospheric response will be. East Africa faces a different and inverse risk. El Niño enhances the October through December short rain season over the Horn of Africa and the East African highlands through its influence on the Indian Ocean Convergence Zone and the positioning of the Intertropical Convergence Zone during the Northern Hemisphere autumn. In November 2023, El Niño enhanced rainfall killed more than 100 people in Kenya in a single month and displaced hundreds of thousands across Somalia and South Sudan. This arrived in communities that had spent 2021 and 2022 inches severe drought, driven by the La Niña that preceded the 2023 event. The same sequence is now repeating. The 2025-2026 La Niña produced drought stress across parts of East Africa in 2025, and the incoming El Niño is now positioned to produce flooding in the same regions during the 2026 short rains season. The logistical and infrastructure capacity to simultaneously recover from one ENSO phase extreme and prepare for the opposite extreme arriving within 2 to 3 years does not exist in the affected communities. The response system in East Africa is not built for back-to-back opposite extremes with inadequate recovery intervals. Australia is entering preparation mode. The Australian Bureau of Meteorology issued El Niño watch guidance as the La Niña dissolved through early 2026. The Bureau's seasonal climate outlooks for the coming months show elevated probability of below-normal rainfall across Queensland, New South Wales, and Victoria, the 3 states that together constitute Australia's agricultural heartland and the region that burned most catastrophically in the Black Summer fires of 2019 and 2020. Those fires burned more than 18 million hectares, killed approximately 3 billion animals, and produced smoke plumes that were measurable in atmospheric chemistry data across the Southern Hemisphere. Fire risk in southeastern Australia is a function of fuel load, the amount of dry, combustible vegetation accumulated across the landscape, and soil moisture. Below normal rainfall increases both factors. It dries existing vegetation, it reduces soil moisture, and if sustained across a summer, it can produce the conditions where fire behavior exceeds the capacity of any suppression system to contain it. Australia's fire managers do not wait for drought to materialize before adjusting preparedness. The Pacific subsurface data is sufficient. The incoming event is already shaping autumn resource allocation decisions. Agricultural commodity markets that span continents are already processing the El Niño signal in their pricing and procurement structures. Rice is the most directly exposed of the major staple crops. The South Asian and Southeast Asian monsoon systems, which deliver the seasonal rainfall that makes irrigated and rain-fed rice cultivation possible across India, Bangladesh, Thailand, Vietnam, Cambodia, Indonesia, and the Philippines are sensitive to El Niño in ways that translate directly to production volumes. El Niño's influence on the Hadley circulation and the position of the intertropical convergence zone during the southwest monsoon season tends to reduce rainfall over parts of the Indian subcontinent and archipelagic southeast. Asia, the combined agricultural systems of which produce the vast majority of the world's rice supply. During the 2023-2024, El Niño, India, the world's largest rice exporter, accounting for roughly 40% of global rice trade in a normal year, imposed export restrictions in late 2023 inches to response to domestic supply concerns, driven in part by monsoon variability. Rice prices reached multi-year highs globally. Vietnam and Thailand, the second and third largest exporters, reduced their export commitments in response to reduced harvest projections. The populations most exposed to rice price increases are concentrated in sub-Saharan Africa, South Asia, and Southeast Asia, the same populations most directly affected by El Niño's precipitation anomalies, and they spend the highest proportion of household income on food of any populations on Earth. The convergence of supply reduction and demand concentration in the same geographic zones is not a coincidence. El Niño systematically reduces supply precisely in the regions where the demand is least elastic and the households are least able to absorb price shocks. Coffee, cocoa, wheat, and palm oil each carry their own El Niño sensitivities. Indonesian and Vietnamese coffee production, which together supply a substantial fraction of global Robusta coffee output, is vulnerable to the drought conditions El Niño produces over maritime Southeast Asia. West African cocoa production, concentrated in Ghana and Côte d'Ivoire, is sensitive to the West African monsoon disruptions that El Niño can produce through its influence on the Atlantic ITCZ. The simultaneity of stress across multiple commodity systems in a single El Niño event is not unusual. It is the normal functioning of El Niño's global teleconnection network, but the intensity of that stress is a function of the event's absolute temperature impact, not just its anomaly score. The coral reef situation as this event develops deserves its own careful accounting because the trajectory of global reef systems over the past 3 decades illustrates the rising floor problem with a clarity that abstract temperature data does not. The first global coral bleaching event was documented in 1998, driven by the 1997-1998 El Niño. It was the first time bleaching had been observed simultaneously across multiple ocean basins. Scientists called it a global event because nothing like it had previously been recorded. Approximately 8% of the world's coral reefs died. The event prompted urgent calls within the scientific community to develop global reef monitoring systems, and NOAA's Coral Reef Watch thermal stress monitoring network was built in direct response. The second global bleaching event occurred in 2010, driven by ocean warming rather than a strong El Niño. It was less severe than 1998. The third global bleaching event ran from 2014 to 2017, driven primarily by the 2015-2016 El Niño at its peak. It was by far the longest and most severe in recorded history to that point. Approximately 15% of the world's coral reefs died. On Australia's Great Barrier Reef, the world's largest coral reef system at 2,300 kilometres, the 2016 bleaching killed approximately 30% of the northern section. Australian Institute of Marine Science surveys found bleaching on more than 90% of surveyed reefs in the northern and central Great Barrier Reef during 2016. The system that emerged from that event was structurally degraded in ways that will require decades to reverse, if full reversal is even possible. The fourth global bleaching event began in 2023-2024, confirmed by NOAA's Coral Reef Watch as the most geographically extensive on record. It covered reef systems across the Indo-Pacific, the Atlantic, and the Caribbean simultaneously, with bleaching alert level thermal stress reaching reef systems that had been considered marginal in previous events. That fourth event has not fully resolved as this fifth significant El Niño thermal stress begins loading. The reefs that survived 2016 and were bleached again in 2020 and 2022 and 2024 are not healthy reef systems with full thermal buffers. They are reef systems in various states of partial recovery, carrying less structural reserve than fully recovered reefs, and with thermal tolerance thresholds that stressed populations have in some cases permanently reduced. The recovery time between the third and fourth global bleaching events was 8 years, far less than the 7-year gap between the second and third. The recovery time available before the thermal stress of the 2026 El Niño begins imposing on reef systems is being measured in months, not years. NOAA's Coral Reef Watch is already showing elevated sea surface temperatures across portions of the Indo-Pacific Reef Zone in April 2026, before the full El Niño anomaly has established itself at the surface. The background ocean temperature is already doing work that historically required El Niño's anomaly to accomplish. When the anomaly arrives on top of that background, the question is not whether bleaching will occur across major reef systems, it is how extensive the mortality will be. The open scientific questions surrounding this event are genuine and deserve honest treatment rather than either false certainty or manufactured alarm. The spring predictability barrier is a real constraint on current forecast confidence. April and May are the months when ENSO model skill is lowest because the equatorial Pacific is in a transitional state where small perturbations in the atmospheric forcing can shift the trajectory significantly. The ECMWF median forecast of plus 2.2 degrees Celsius is the center of a range, and that range includes outcomes meaningfully weaker than plus 2.2 and outcomes meaningfully stronger. Once the spring predictability barrier passes in late May, forecast confidence will improve substantially and the peak intensity uncertainty will narrow. For now, the honest assessment is that strong El Niño conditions are the most likely outcome, with a meaningful probability of very strong to super El Niño conditions and a substantially lower but non-zero probability of a moderate outcome. The interaction between the incoming El Niño and the northeastern Pacific blob introduces forecast uncertainty for Western North America that standard El Niño guidance does not fully capture. This is documented in NOAA's own materials and needs to reach the people making practical decisions. The calibration validity question whether the historical El Niño impact models built on the 1950 to 2010 observational record retain predictive accuracy for events developing on an ocean temperature baseline that has shifted outside the historical range is the deepest and most consequential uncertainty. If the calibration has drifted past a practical threshold, the models are systematically underestimating impacts from every strong El Niño event on the current baseline. The 2023 data, where a nominally moderate strong El Niño produced outcomes consistent with or exceeding the historical response to a very strong event, suggests the calibration has already drifted. Significantly, the 2026 event will test it again, at potentially higher intensity. El Niño has been part of the Earth's climate system for at least 10,000 years. Ice cores from the Andes and lake sediment records from across the Indo-Pacific document the oscillation cycling through warm and cold phases across the full Holocene. It is not a feature of the modern industrial era. It is a fundamental expression of the coupled ocean-atmosphere dynamics of the largest ocean on the planet, operating on timescales governed by the travel speed of Kelvin waves and Rossby waves physics that does not respond to any forcing on human timescales. What does respond to forcing on human timescales is the baseline the oscillation operates on. 3 data points illuminate the trajectory with documentary precision. In 1997, 1998, a plus 2.3 degree El Niño produced the then highest annual global mean temperature in the instrumental record. In 2015, 2016, an equally intense plus 2.3 degree event produced a higher annual global mean temperature than 1997's event, despite the same anomaly magnitude. In 2023, 2024, a plus 2 to 2.1 degree event, nominally weaker than both predecessors, produced a higher global annual mean temperature than either of the stronger events that preceded it. The anomaly intensity did not increase monotonically across those three events. The baseline did, and each time the baseline increased, the same anomaly produced a higher absolute temperature, crossed more thresholds, and generated more severe downstream outcomes than the historical calibration framework predicted. The pattern is not ambiguous, and it is not dependent on a particular model or a particular scientific framework. It is present in the raw observational record, in the direct comparison of three measured events, each producing a higher global temperature result than the previous one despite no consistent increase in anomaly magnitude. The 2026 event is projected to reach anomaly values comparable to or exceeding 2023's peak on an ocean baseline that is at least as warm as 2023's, and by some metrics, warmer. The logical extension of the documented three-event pattern is that the 2026 event, if it reaches the ECMWF median forecast of plus 2.2 degrees, will produce global temperature outcomes more extreme than the 2023 event did on the same rising trajectory that each of its predecessors established. What that means for the systems already at or near their operational limits is not speculative. Coral reefs that bleached in 2024 face a new thermal event before they have recovered from the previous one. Fisheries along the Humboldt Current face the closure of the warm anomaly window for the second time in 3 years before the ecosystem has re-established the cold upwelling that sustains it. Agricultural systems across the tropical monsoon belt face the disruption of growing season rainfall for the third strong El Niño event in a decade. Emergency response systems in East Africa and South America face the prospect of opposite extremes arriving on populations that have not recovered from the previous extreme. Every one of these statements is grounded in the documented record of what previous El Niño events have produced on lower baselines. The 2026 event will test all of them on a higher one. The forward question this event produces does not resolve within the lifetime of the event itself. The Kelvin wave currently crossing the Pacific will arrive, the surface will warm, the Walker circulation will weaken further, the atmospheric arm will lock in. NOAA will formally declare El Niño conditions, likely before July. The event will peak, probably between August and November, based on model consensus. Its teleconnections will redistribute rainfall and temperature anomalies across the globe through the following year. And then it will decay, giving way to neutral conditions, or La Niña, and the attention cycle will move on. But the question the event leaves behind is not about this specific event's peak or decay. It is about what the baseline will read when the next event of comparable magnitude develops. If the global ocean continues accumulating heat at the rate documented in the Argo record, the baseline in 2029 or 2031 or 2033, whenever the next strong El Niño develops, will be higher than today's baseline by a measurable amount. The same anomaly that is projected to make 2026 a record or near-record year will, on that future baseline, produce outcomes more extreme than the 2026 event produces. The bleaching threshold will be reached at lower anomaly values. The drought severity thresholds will be crossed faster. The food security impacts will be larger because the systems at risk will have had less recovery time between events. The recovery window is not simply compressing between events because El Niño events are becoming more frequent. It is compressing because the rising baseline is extending the period during which each event's absolute temperature impact crosses actionable thresholds, effectively lengthening the harmful phase of each event, even if its duration, as measured by the anomaly index, remains similar. An El Niño that maintains bleaching threshold temperatures across the Great Barrier Reef for 12 weeks, based on the 2026 baseline, may maintain the same threshold temperatures for 16 weeks on a baseline 0.4 degrees warmer, because the ocean takes longer to cool back below a threshold that has been set higher. The extra weeks are the mechanism by which the recovery window shrinks. There is a number that should be sitting in the front of every mind that engages with this story. It is not the Niño 3.4 anomaly score. It is the reading from the Eastern Equatorial Pacific as of the 15th of April 2026, before the event has formally begun. Plus 1.8 degrees Celsius in the Niño 1+2 region, the ocean closest to the Peruvian coast, the leading edge of the incoming warm water mass. That number represents the front edge of something that has been loading in the subsurface Pacific for months, the 6 to 7 degree anomaly in the thermocline layer following behind it, the second Kelvin wave in the western Pacific that is still in the water, the warm water volume in the upper 300 meters elevated above the historical mean for this time of year, the La Niña that collapsed faster than anticipated and transferred its accumulated warm water reservoir to the east with unusual energy, the global ocean heat content at its highest recorded level, providing the baseline onto which everything else is being added. The instrument that is measuring plus 1.8 degrees Celsius in the Niño 1+2 region today is the same TAO, Triton buoy network, built after the 1982 forecasting failure. It has been collecting data continuously since the early 1990s. It has watched every El Niño of the modern era develop, peak, and decay. It recorded the 1997 event, the 2015 event, the 2023 event. And right now, in the final days of April 2026, it is telling a story in the language of tenths of a degree Celsius that takes months to fully read, but that has only one direction. The strongest El Niño in decades is not approaching. It is already in the water, moving east at the speed of physics, carrying in its leading edge more thermal energy than any comparable subsurface anomaly in the modern observational record. The models that are projecting plus 2.2 degrees by September are not projecting a catastrophe. They are projecting the median outcome of a physical system that has already been set in motion by forces that were active months before today. What those models are less equipped to project, what no model has yet fully incorporated, is what it means for every historical El Niño impact calculation to be running on a baseline that the historical record was not. Calibrated to the coral bleaching risk, the fishery collapse probability, the monsoon disruption severity, the flood and drought intensity across El Niño sensitive regions. All of those risk estimates are anchored to a historical ocean that has warmed beneath them. The wave is already moving. The leading edge has arrived at the coast. The second wave is in the water. The planet's largest ocean, on its warmest recorded baseline, is in the process of reorganizing, and the instrument measuring it is already collecting data for what comes after this.